Okay, so problem 17 on recitation 10. The question asks what the pH of a 0.5 molar solution of sulfuric acid is, and what is the pOH? So again, one of the first questions that we're going to ask ourselves, we know that this is a polyprotic acid, or well, at least when you look on the formula sheet for sulfuric acid, you will see right here that sulfuric acid is H2SO4, so it's a diprotic acid and it has two hydrogens that it can donate. And the next question that we're going to ask ourselves is it a strong or a weak acid? Remember the last one up here, we saw that the dissociation constant was 7.11 times 10 to the negative 13th, and we consider that a weak acid. If we go back to the formula sheet, we will see that we actually have both the first proton and the second proton, the dissociation constants for the first proton leaving and the second proton leaving. And for the first proton leaving, we find the Ka value is 1 times 10 to the third, and the second Ka value is 1 times 10 to the negative second. So we'll write that right here. 1 times 10 to the third and 1 times 10 to the negative second. Now the difference between a weak and a strong acid, really, and especially a polyprotic acid, is you remember how with the weak polyprotic acid we only considered this first proton that dissociated because these Ka values for the sequential protons that dissociate is so small that we hardly get any protons that dissociate, so we don't even factor them in. However, completely opposite of that, with a strong polyprotic acid, this Ka value is so high that as soon as we put it into the reaction vessel, that first proton is going to jump right off, and it's going to be so fast that we'll just say for this case that we can't even measure it. And so we are actually going to focus mainly on the second dissociation constant, or Ka value, but we do have to take into consideration that proton that already came off. So for our Rice table, we're actually going to ignore this equation, and we're going to use this bottom one. So RICE, and we know that water is not going to be included in the equilibrium expression. And what we have to realize is as soon as we put that acid into the solution, that first proton already came off and left us with this HSO4 minus, or what we call the hydrogen sulfate ion. And then you write your equation based off of the information that you're given here. But what that means is this H3O plus concentration, it completely dissociated, which is the definition of a strong acid. And so we have to assume that we start with 0.5 moles, a molar of HSO4 minus, but then we also already have 0.5 molar of H3O plus because from that first proton that already came off. Now, if you're not following what I'm saying, send me an email or just relook over this. But we already have an acid, the first proton that dissociated, and you have to remember that for strong acids. You'll see the same correlation with strong monoprotic acids like HCl, except because there's only one proton with HCl, we wouldn't technically have this 0.5 right here. However, because we have a second proton, we do include that 0.5. So moving on, we have 0 SO4 minus, because that's the conjugate base of this acid. It's not the same as HSO4 minus. And so we know that we are going to lose X, gain X, gain X, at equilibrium of 0.5 minus X, and then 0.5 plus x. And like I said, we're going to use this Ka value. We have 1 times 10 to the negative second equals 0.5 plus x times x over 0.5 minus x. And so now is just our typical algebra. We're going to multiply this over, and we're going to get, I did this earlier just to make it faster, so we are going to get 0.005. 0.005 minus 1 times 10 to the negative second x equals 0.5 x plus x squared, right? And from here, we're going to try to get everything in order of the quadratic formula. So x squared, x, and then just the regular numbers. So I'm going to take everything and move it over to the right side, and I get 0 equals, I'm gonna swap these two because I like to have them in order of A, B, C. So x squared, so 1 times 10 to the negative second, we will have to add that plus 1 times 10 to the negative second to both sides. And that'll just give us 0.51x. Do it in your calculator, pause it and do it, but 0.51x, and then minus 0.005 because I just took this value, subtracted 0.05 on this side too to cancel it out. And now plug that into your quadratic formula. Be careful if you're using just a scientific calculator. But remember A, B, C, and do not forget that this is negative 0.005. And you should get x equals some weird number and then 0.009622. 0.09622. And because the question asks us to find the pH, we know that we're going to take the negative log of whatever the equilibrium value of H30 plus is, or the hydronium ion concentration. So we do 0.5 plus 0.009622 equals 0.509622. Yeah, sorry, that should have been easier than I thought. 509622. We take the negative log of that value, and that should give us 0.2928 pH. 0.2928 pH, and we just take 14 minus 0.2928 equals, I'm just going to look over here, 13.7 pOH, right? Because it's 14 minus whatever the pH is, the pOH. And make sure you round to sig figs, right? Sorry, that should not be. And that should be your answer. So about 0.3 pH or 0.29 pH and 13.7 pOH. Email me if you have any questions, but good luck.